Bien, bonjour à tous. Michael Sinatra, le directeur du Centre de recherche interuniversitaire sur les domaine numérique de l'Université de Montréal. Très heureux de vous accueillir ce matin pour notre dernier événement de la série 2022 en collaboration avec le département d'Histoire de l'art et d'études cinématographiques de la FAS. J'ai eu le plaisir d'organiser une série avec Martha Bonny et Emmanuel Château-Dutier de ce département-ci. Et ce matin, avant notre dernier conférencier, j'ai le plaisir d'accueillir mon doyen Frédéric Bouchard qui va venir nous dire quelques mots.
J'ai aucune idée.
Oui, c'est bon, c'est là, c'est parfait.
Oui, c'est parfait. Merci, Michael. Monsieur Stefaan van Liefferinge, directeur du Media Center for Art History à l'Université de Columbia. Chers collègues, chers invités, chers participants en ligne, je suis ravi d'être avec vous ce matin pour inaugurer, en fait, pour le 3e cycle de conférence Midi Humanité numérique, et qui, cette fois-ci, est organisé en partenariat avec le département d'Histoire de l'art et d'études cinématographiques. Notre département d'Histoire de l'art et d'études cinématographiques a de nombreux projets en lien avec le secteur des humanités numériques et plusieurs des professeurs font partie du CRIN. Je mentionne, j'espère oublier personne, mais Christine Bernier, Carl Terrien, Martha Bonny et Emmanuel Château-Dutier. Merci d'ailleurs à Martha et Emmanuel d'avoir co-organisé avec Michael la série de cette année. Exemple récent de l'implication du département dans les humanités numériques, le projet des nouveaux usages des collections dans les musées d'art porté par Joanne Lamoureux, professeure titulaire au département d'Histoire de l'art et d'études cinématographiques. Ce projet a obtenu une subvention de partenariat CRSH et on en est ravis. Et un secteur entier du projet concerne les humanités numériques. Afin de soutenir ce projet, l'ouvroir laboratoire de recherche dirigé par Emmanuel Château-Dutier et hébergé dans les locaux du CRIN fournit à l'ensemble de l'équipe un équipement de pointe pour conduire des recherches, mais aussi pour expérimenter et développer de nouveaux usages pour les collections numérisées qui utilisent le web, les techniques de visualisation 3D et la réalité virtuelle et augmentée. En fait, toute notre réalité semble de plus en plus virtuelle et de plus en plus augmentée, mais ça, c'est une autre histoire. Ce sera peut-être un champ de recherche. En fait, vous le faites peut-être déjà. Ce projet donne aussi l'occasion de créer une infrastructure éditoriale solide pour l'encyclopédie numérique et de produire 3 développements informatiques qui seront mobilisés dans les différents axes de cette recherche, soit d'abord la mise en place d'une plateforme collaborative de travail pour étudier les archives, la création d'un outil numérique consacré à la documentation des accrochages de collections et la création d'une librairie JavaScript dont le but est de faciliter la production et le déploiement de dispositifs d'exposition numérique et de l'illustration de l'encyclopédie. Cette création permet de doter le Canada d'un équipement de recherche dédié à l'expérimentation et au développement d'innovations dans le domaine de l'histoire de l'art et de la muséologie numérique, dans lequel notre faculté compte jouer un rôle de leadership intellectuel significatif. À l'ère du numérique, la recherche en lettres sciences humaines se décline sous plusieurs volets que vous connaissez bien parce que vous y participez. On parle de théorisation, production des contenus et de réception. Le regard de plusieurs disciplines est primordial lors de ces 3 étapes. C'est pourquoi le 18 février dernier, la Faculté des arts et des sciences lançait officiellement le Carrefour en culture et création numérique, le C3N, qui a pour mission d'offrir notamment un cadre d'animation de la recherche en culture et création numérique, favorisant ainsi le travail interdisciplinaire si cher à notre faculté. La Faculté des arts et des sciences est toujours ouverte à de nouvelles collaborations et la venue de notre collègue Stefaan van Liefferinge est une magnifique opportunité de discuter plus en profondeur des collaborations autour de la recherche et de l'enseignement en humanité numérique dans nos institutions respectives. Pour finir, je vous annonce en avant-première mondiale que cette série de collaborations entre le CRIN et les départements de la faculté se poursuivra l'an prochain avec le département d'anthropologie qui participera à l'animation scientifique. En terminant, et là, je parle à nos collègues de la faculté, vous avez les exercices de planification stratégique au sein de chaque département. Ça sera très important de nous nourrir, donc au sein de vos départements, mais aussi la faculté, comment nous pouvons ensemble jouer un rôle d'autant plus structurant dans le secteur des humanités numériques On est très, très fiers de notre contribution depuis des décennies au scholarship en lettres, sciences humaines et sciences sociales, bien sûr dans d'autres secteurs, là, mais c'est les secteurs qui nous occupent aujourd'hui. Et les humanités numériques, en quelque sorte, on doit réfléchir comment poursuivre cette contribution-là à la hauteur des besoins de la connaissance et de notre société. Donc, je vous invite vraiment à contribuer à cette réflexion-là pour nourrir notre planification facultaire. Donc, bienvenue à la Faculté des Arts et des Sciences et bonne conférence à toutes et tous. Merci beaucoup.
Merci beaucoup. Merci, monsieur le doyen. Et j'invite maintenant ma collègue Christine Tatton, qui est aussi membre du CRIN et dirige avec Emmanuel le laboratoire Ouvrard, à dire quelques mots pour présenter notre invité.
Bonjour, c'est un grand plaisir à introduire notre collègue Stefaan van Liefferinge. Stefaan a fait ses études du bac en informatique. Il a fait une maîtrise en physique et en informatique. Et il a fait un doctorat en histoire de l'art médiéval de l'Université de Columbia. Ses domaines de spécialisation sont l'architecture gothique, les nouvelles technologies et les médias numériques et l'histoire des sciences. Il a effectué des travaux de terrain à Notre-Dame de Paris, à la Cathédrale de Clermont et dans plusieurs autres églises gothiques anciennes de Paris et de ses environs. Il a notamment lancé un projet alors qu'il était professeur adjoint à l'Université de Georgia, qui utilisait l'intelligence artificielle pour comprendre l'histoire de l'architecture médiévale. Et je pense qu'il était un des premiers qui a vraiment utilisé cette deep learning dans le champ de l'histoire de l'architecture. Réunissant les pratiques du conseil en informatique à l'université, Stefaan van Liefferinge apporte l'ensemble idéal d'expérience à son rôle de directeur du Media Center for Art History at Columbia. Le centre développe et appuie les travaux de terrain et les projets de recherche qui documentent, présentent et interprètent les œuvres, l'architecture et les sites culturels. L'un des principaux objectifs du centre est de faire progresser les humanités numériques, d'explorer les technologies numériques au service de la recherche en histoire de l'art et de préserver et développer sa collection visuelle. Aujourd'hui, Stefaan va partager avec nous certaines de ses réalisations. Bienvenue, Stefaan. Merci beaucoup.
Okay, so first of all, thank you very much for these very kind introductions. I would like to thank, the Faculty of Arts and Sciences, Faculté des Arts et Sciences, Monsieur le doyen Frédéric Bouchard. I would like also to, share thanks with Michael for director of the CRIN also for inviting me. I would also like to thank Christine and to thank Emmanuel for having me here. It's a great pleasure, and thank you also for being so generous with your time and for for this nice, very pleasant stay. Good. So I will do my presentation in English. I will be more than happy to talk to you in French. I start with a little apology because I could do the presentation in French, but the problem is I've been done my work in English for the past 20 years, and it is with the technical terms might be a little bit tricky to jump around, and it might be end up more complicated. So again, thanks for having me here. I will start now with this presentation in which I plan to present mainly research project that I had over the past years, and also introduce you to a little bit how it fits with research at the Media Center for Art History at Columbia University, of which I'm the director. Good. So we're in Montreal. We're at here at the UDM. So let's first go there, up, and then click here and briefly start. So I titled this presentation "Research in the Architectural Past: Logic, Images, Medieval Construction," because these are like the the main axis of my research in the past. And As I just mentioned, I'm the director of the Media Center for Art History. It's a center that was established already in 1993 under the leadership of Professor Stephen Murray at Columbia University. The Media Center has evolved in a center where we work on collections, meaning we collect visual materials for a faculty in the Department of Art History, and we work also on individual projects. Feel free to visit our website. You can find most of the information about the Media Center there. It will also, if you want to have a sample, an idea of the type of media that we are manipulating and that we're working with, you can find this right on our front page. Again, in this presentation, there will be no time to talk about all these different technologies that we use. In a nutshell, we use deep zoom images. We use 363-degree images, which was something important because basically these are the type of images that now we use for virtual reality. And we also use photogrammetry models, so 3D reconstructions, together with also 3D modeling for creating virtual reconstruction of archaeological sites. And this is just to give you, a couple of examples of what happens at the Media Center. As a background thought about digital projects, I've been working, with digital and computational projects for about 20 years now, since I started my PhD at Columbia University. One of some reflections that I have about it is that I think that it's important to realize that every project is specific and every solution is specific. There is no grand scheme of digital, humanities, of digital technologies. There are many fields that are, starting to or already working for a while with digital humanities. Think about the size of the humanities, all the different fields. Think also about the size of, of the computer sciences, how many different fields there are in computer sciences. You have a combinatorial explosion of possibilities. And I think that one of the key elements is, when you approach a project, is always to try to find, well, what is the right match? What works well? And then to try to work with that specific project. What is very positive, I believe, and it's maybe not a recent development, but something that I observe, is that we have more and more accessibility of technology. So we have people who are not specifically tech people who are able to do very good work in technologies. And this goes, of course, way beyond just, using a word processor or just using a digital camera. So the field is really changing, and we are, in my opinion, going towards a tipping point. About 10 years ago, I was skeptical where it was going. Now I think that we are really going to something that is different, and it will be very hard not, to keep the digital humanities inside of the equation of the humanities. Good. So what I will present now, again, is it's a sort of medley of different projects. The first project was called the ARC project, the architecture represented computationally. Christine kindly already referred to this project. It was led at the University of Georgia together with the Institute for Artificial Intelligence. And the goal basically is how can we have a computer understand Gothic architecture, a Gothic cathedral? So this was project number one. I will introduce it more in details in a couple of seconds. A second project that also harnessed the power of AI is a project that was called the Art Historical Image Collection at Columbia University. We had the pleasure, so the Media Center had the pleasure to present it at the DH North conference in 2020. So I will briefly talk about also some techniques from AI that we used for this project. It's about a slide collection, about a very large slide collection that we host at Columbia University. And basically, we didn't really know what to do anymore with these image resources, so we tried to find solutions for it. Following this, I will talk about two projects. One that was for the Media Center itself, which is the map in Gothic France, which is probably the largest project that was ever led at the Media Center. It was a project to bring into a digital map, all the churches in France and in England, and basically Gothic buildings in Europe. I will probably not present this last project here. But I would like to talk about this one because I find that this project, which was in collaboration with my colleague Michael Davis, who was at Mount Holyoke College, drawing flyers at the Clermont Cathedral, I find shows that basically things are changing. There is no need for a big, technological knowledge to do a project where we really can, understand a building in a different way than we did, for example, even 10 years ago. So I hope this project will illustrate this. Good. So let me now first go to the architecture represented computationally project that was at the University of Georgia. So we are in the south of the United States, in Athens, where we have this large research university. I was lucky to be there for about 5 years. Let me take you to this project. Good. So architecture represented computationally was from 2008 until 2012. For the participants, and I think it was of course I'm biased, but I thought it was a beautiful project because I found it a truly, interdisciplinary project in the sense that we had students from the School of Art, so the art history department is part of the School of Arts at the University of Georgia. There was me, Stefaan van Liefferinge, and then a graduate student, Rebecca Smith, but then also students from the Institute for Artificial Intelligence, so students in computer science who actually produced a master's, so a master's thesis based on this project. I would especially like to, single out this student who was very productive and created in the end a system that would work. My colleagues, Michael Covington, a specialist in natural language processing, and Walter Potter, a specialist in robotics, also, who was the director of the Institute for Artificial Intelligence. This project got some funding. We had the National Endowment for the Humanities, the University of Georgia Research Foundation, and also we had we received the generous funding from the University of Georgia's venture funds. What was the project about? Well, for the principal elements in this project were, on the one hand, Gothic architecture, descriptions of buildings, and techniques from artificial intelligence. As I already mentioned, the idea was, well, how can we, have a computer understand a Gothic cathedral? A Gothic building, a Gothic cathedral, of course, it's a structure, it is architecture, and we manipulate specific, terminology as an architectural historian, when you talk about a Gothic building, you manipulate specific terminology about it, you describe it in a certain way. The idea was actually to see how can a computer, maybe through the means of artificial intelligence, be capable of also doing the same sort of job as the architectural historian who is confronted with a building and who can talk about this building. Just for the technological part, we selected Prolog. There were two reasons for it. First of all, that is that Michael Covington, so one of the partners in the project, was a specialist in Prolog. And second, also, we wanted to have the computer, to make inferences and think about the architecture that was described. And Prolog was well suited for this because it's a programming language that embeds query and inference. So there's an inference engine that is inside of this that is part basically of this programming language. As I just said, we wanted to test the capacities of AI to understand architectural rules, the logic. It will become more clear in a couple of seconds what this means, and also reproduce in a computer the mental image of a Gothic cathedral. Again, this will become more clear in a couple of minutes, and then finally make a computer reason about these buildings. For the potential outcomes, why I thought that this project would be interesting, well, when we describe architecture, when we talk about, for example, this room, we'll say there are green panels here, there are neon lights on the ceiling, etc. Sometimes, we make a description of a building, and sometimes errors are made in descriptions of buildings, even, even by specialists and when they're written also, we thought that maybe, this program could be able to check actually, well, is this actually, the correct description of what the architecture actually is? Another possible interesting point also is that, well, it was not limited to Gothic. I mean, Gothic, which was Gothic, just like which was Prologue, because of it was a specialty of one of the members of the project. Gothic architecture is my field, so it seemed to be logical to work with Gothic architecture. Something also that could be interesting was, well, sometimes we have descriptions of buildings, but many buildings have been destroyed also. For example, during the French Revolution. It might be interesting to go see and find if we can find descriptions of buildings and that we could recreate actually the buildings that have disappeared. So if we could have a computer, trying to recreate these buildings. Finally, a final or a long-term goal of this project was maybe can we have an automated translation of a description? So say someone would be describing a building and automatically, somewhere a computer would, start to build the building in a 3D model. And I have to, to make a reference to the World's Eye project by Bob Coyne here, which is not, about Gothic, but which also, translates, text into images. I also have to, say that this project was highly influenced by a work by William Mitchell from MIT, which is called The Logic of Architecture, which was sort of, a book that it was already from 1990, so about 15 years before the ARC project. And a lot of elements in it also were already discussing, well, how can we describe, architecture by, with computing technologies. Now, why Gothic cathedrals? Well, as I said, well, first of all, Gothic cathedrals are my area of specialization. But at the same time, also, they were quite suited for this research. They were a good fit to have a computer, think about Gothic cathedrals. On the one hand, they are challenging because they are complex products of human creativity. I mean, a Gothic building is an extremely complex structure, and you can spend, 10 lifetimes working on it and studying it. At the same time, also, if it's a complex product of human creativity, it also follows some constraints. They can be physical and design constraints. So you have some sort of generic model that exists there. This will be more clear in a couple of seconds. And third, also, well, there are descriptions of Gothic buildings. Art historians now for a few centuries have been, describing Gothic buildings. So we have textual descriptions of these buildings. Move to the next slide. Good. So, well, just as an illustration, Notre Dame of Paris, as you can see, it's very complex building, but there are some constraints. I mean, you cannot say that, for example, that the roof is not at the, that the roof is at the top of the building. Everybody knows that. So there are some constraints with this building. There are some rules that are followed, and they might seem, self-evident. But again, what we find self-evident is not always what a computer finds self-evident. So for physical constraints, again, it repeats a bit what I just said. So we have inside of the building, inside of Notre Dame here, we have supports, these columns, and then at the top of the building, we have the vaults. Everybody knows that the vaults will be above the columns. So if I tell you Notre Dame has vaults, and as columns, nobody will place the columns above the vaults visually into the mental image that you are creating of the building. For the design also, Gothic buildings usually follow a number of rules. I mean, like there are usually pointed arches, or at least arches that you have. And there's also the repetitive aspect of the architecture. So we have repetition here bay by bay of the building, and we can see that we have this for different cathedrals, here for Notre Dame and here for Noyon Cathedral. So again, they are, products of human creativity and extremely complex buildings. At the same time, there are some rules. So they are a good subject actually for a computer to, to study and to see whether we can have a computer understand a building. Another aspect of it is next to these constraints also, physical and design constraints, is there is a vocabulary that is manipulated by our architectural historians. So we use very specific terms to describe these buildings. So for example, here we know that this is the nave arcade. This is called the triforium in this jargon. Here, this is called the clerestory. So a little bit like, medical language, there is something that, that is also well, that can be, told to a computer. Are the words that you need to manipulate to try to understand. I mean, when I said like medicine, I'm also thinking about, I don't know whether you're familiar with medical coding also, which is the whole system, to classify diseases and so on, and diagnosis, so on. So there is something similar that can be done with these Gothic buildings. These different elements that I just mentioned, these constraints and this, vocabulary, leads to a specialized language. So, for example, here the plan included a 5-aisle nave, 5 double bays, a wide non-projecting transept, and a choir of double bays flanked by double aisles, which continue in a double ambulatory. This is very boring to read. That's very clear. At the same time, it's supposed to be precise also. So, if you look at this is the plan of Notre Dame. And you have a description of the plan of Notre Dame here. So you have the wide non-projecting transept. You have the choir with the double bays each time here. So in here, one here. And then you have also this flanked by double aisles here. And it continues in a double ambulatory, which is the east section here of the building. So we see that there is a structure in the way that these buildings are described, just like these buildings are structured. Another example is for the elevation. So we go now from the bottom to the top. We have an arcade, gallery, triple bays, oculi, and clerestory windows. We have them here by these little color dots. But observe, and this is actually because this bay was a restoration by Viollet-le-Duc in the 19th century of Notre Dame. The other bays here, we only have 3 elements of it. As you can see, this element is missing. The point that I want to make is you get immediately to something that is sort of challenging for a computer. It's not just a 3D model. It's not just you say to the computer, okay, if you have a bay, you have these 4 elements. The computer has to be able to understand that, well, sometimes it will change. Sometimes it will not be as simple as this. And sometimes, the computer has to think, well, I have to be capable of going back and rethink what I was just saying and maybe also modify it. So, as I just said, there are some elements that are not always present. So, the knowledge representation of the knowledge or the knowledge base has to be flexible. It has to be, we have to be able to change it. Sometimes also in the description, descriptions are very compact of architecture, but we take a lot, there are a lot of assumptions that we make. That means that, we are not going to mention every element that is there. If you say that there are columns in the building, automatically we are going to fill in some elements where you go and say, well, there are plinths under those columns. They don't stand just on the floor, or there are capitals on those columns. So again, this is sort of a challenge for a computer. So it assumes a lot of knowledge. This goes back to what I just said. It's even a step further. And this was challenging, is that there is a lot of defeasible or what is called non-monotonic reasoning, meaning that when you look at architecture and you describe something and you say, for example, well, okay, in the right corner there's a door, and then you imagine that the ceiling has just be above the door, but then someone else adds, well, actually, above that door there is a high window. Automatically in our mental picture we will have the door. We will have changed our, the way that we conceive it. We will add the window and we will raise the ceiling there. So that's non-monotonic reasoning. We deduct something and we think that is what it is. But then when elements are added, we review all the time, what is described. Okay. And that's another challenge for a computer also to do this. This is absolutely not so self-evident for a computer. How to deal with individuals is what I mentioned also. There are some elements that we will not that we don't mention. And so in a cathedral, every column has a base. What does that mean for a computer? Every column has a base. Computer works with numbers also, with specific entities always. So for a computer, this would be chair 1, chair 2, chair 3. We just say, well, there's a row of chairs here in front of me without, the computer being capable of knowing exactly what are you talking about. So again, this all illustrates, why this was, I think, an interesting case study for a computer. Where did the project end? And I have to, to go a little bit faster here. Well, I just want to give a case, an example. So in the end, what we had is that we had a system that was implemented and actually was working. The project was shelved in 2012, but I'm still, working on this project. But I would like just to give an example, of a case study. So where you have, a specialist who's been describing a building, and also, I also want to illustrate, how challenging actually these descriptions can be. I've just leave this on the screen for a couple of seconds. If you read it, you will say, well, I don't have any idea what's going on here. I don't have any idea what we are talking about. I'm exactly the same. Okay, or it will take me quite a lot of time to process it. To help us, what we can have is, for example, have an image that helps us. We're going to, as I already did with the plan of Notre Dame, to look at the plan here in this case of Clermont-Ferrand and at the description. Now, I'm not going to go through the whole entire description, but just, to point out something that might be challenging for a computer, and that the program as it is in the current state is capable of handling, is that, so we have the choir of Clermont composed nearly half of the medieval building. So the choir of Clermont indeed composed about half of the medieval building. And then we have 3 straight bays terminated by a 7-sided hemicycle. So we have 3 straight bays, 1, 2, 3, terminated by a 7-sided hemicycle. Okay. Now, that for a computer is not so self-evident, because if you look, you have 3 straight bays, and I'm stretching it a little bit, I understand that, but you have 3 straight bays terminated by a 7-sided hemicycle, and you don't have the additional information of the plan there that helps you. Well, you might think, well, you have straight bay 1 terminated by a hemicycle, straight bay 2 terminated by a hemicycle, straight bay 3 terminated by a hemicycle. So there is something inconsistent here, at least not something, that the computer really can logically grasp. And just, now I'm going to shift to code, and I must also admit, that the interface that is used is just the online, the command line interface, so it will be a little bit dry in a couple of seconds. But I hope to show you also that the system can grab this here that was developed in this project. How does it work? I mean, again, the main lines are, we start with a default model. So we tell the computer, we give the computer a default model. This would be, all the elements that you have in a Gothic cathedral, in the perfect Gothic cathedral. Your Gothic cathedral becomes a little bit more imperfect for some reasons. Well, you add elements to the default cathedral, or it improves as then you add some elements. You have also to be able to remove, the computer has to be able to remove elements from the default model. And then finally, as I mentioned, we have this non-monotonic reasoning. By adding some elements or removing some elements to what would be the ideal cathedral, well, the computer has to be able, to rethink how, the description of the building that is already constructed. At the implementation level, so actually how it was, the program was implemented, we had a knowledge base, which was again, the place where the repository, the place where we would keep what would be the ideal, Gothic cathedral. We did some strategic choice. We wanted them to be this implementation to be as close as possible to the cognitive process. What does that mean? Well, that that we try to program, to the program that was written, that it would be as close as possible how an architectural historian would, reason about the building. This repeats a little bit what I just said. So we have these different elements that the computer has to be able to do. And we also implemented dictionaries with the vocabulary of architecture that I mentioned in the beginning, different relationships between the elements. Okay? I will come to that in 1 second. The relationship would be, for example, that a capital is above a column. Some meta relationships also, that was like, for example, can this relationship be transitive or reflexive? A relationship that would be transitive, for example, well, say you have a base of a column, you have the shaft of a column, and you have the capital of a column. Okay. Now, if the column is above the base and then the capital is above the column, well, that there will be a transitive relationship with the base of the column also, because the capital, by definition, will also be above the base of the column. There's no way that you can change that. And then also the aspect of subtypes. And finally, dealing, as I mentioned, also with some anonymous objects, just saying we know that every column has a base or has a capital. The engine must be able to make inference based on the basic knowledge that we gave into the machine, that it would be capable, of finding other rules that existed. And I think this is probably the most powerful element that was there. And a change of scope, that meaning that, you could work on a specific part of a building, but then, have the computer change to work on another part of a building. Let's go back for 1 second to the Clermont example. And again, as I said, there would, this is a little bit, a dry presentation of what would be the user interface. This is just, hardcore Prolog implemented. Here, what you have, is the dictionary, basically. So we define relationships. We say that above, for example, is a transitive relationship. As I said, if something is above something, then if there's something else above, well, automatically it's above what was below there, okay? We have also meta relationships, that, for example, we have, if something is immediately above, then automatically it's also above, okay? We also had, objects, subtypes, etc. I will go a little bit quicker here, faster here. And finally, we said, the scope, meaning here, basically, we define a section of the building. If I translate this, so you have what we call the choir of Clermont-Ferrand, call it the choir of Clermont-Ferrand. And then we say there are a number of constraints there. So in the choir, it must have defeasibly, meaning that we can review, the computer can review what he said about this here, that it has exactly two straight bays. Okay? And then, we also had a constraint that it has exactly one easternmost straight bay. Let's move to another step. And again, I mean, I'd be more than happy to provide the details about this. For the sake of time, I have to move forward here. So first of all, we enter the dictionary in the Prolog engine, in the Prolog system. And then we say, to list it, all the elements, you find one object, and you find one relationship that is listed here. In the next step, we do an inference. So we said to the program, okay, think about what we have, fed you with. Think about, what you have. There is this inference that is, it takes 3 rounds, that's fine. And now we do the same list all as we did in 1 second. And then you will see there are 5 objects, there are 9 relationships, there are 12 defeasible facts, 2 indefeasible facts, etc. In other words, based on what we told the computer, based on these basic elements, of having the two straight bays and one hemicycle and one easternmost straight bay, the program has been capable, of finding all sorts of different relationships between these different elements that we gave. So finally, for Clermont, just to illustrate you how it's different, I gave the example, well, if you have, a hemicycle that terminates the 3 straight bays, you could have 1, 2, 3, and each straight bay terminated by a hemicycle. This would be this case. We would say it has 3 straight bays and it has 1 hemicycle. And we say that, the hemicycle terminates the straight bay. What happens? The computer is going to say, well, you have hemicycle, which is labeled by the number 2. I mean, this is, just a random number if you want. By straight bay 3, by straight bay 4, by straight bay 5. In other words, the computer is telling you, well, each of these straight bays has an hemicycle, but that's not the right representation. On the other hand, if we give this here, where we have an easternmost straight bay, which is the last one, where we have the hemicycle, and we query again the system, we see that we have, only 1 hemicycle, and it's only straight bay 2, which corresponds, to the easternmost straight bay that has an hemicycle that terminates it. In other words, it was, a success. The system is capable of correcting this description and is capable of telling us, what, well, might be, not really logical in the description of, this very achieved and colleague and good friend also, architectural historian who wrote that description. Where should we go further? Well, we need more testing. We should load the system. We should, work with many more descriptions also. And then something also that is maybe more crucial is I'm not entirely sure whether Prolog is really the best implementation, more for performance issues. There might be some ways of implementing that might be better, but at the same time also you gain by this logical inference engine that is embedded inside of the Prolog engine. So I don't know. Right now, again, the project is a little bit on the back burner, so I will see where it goes. This was a while ago. It started a project that started in 2007 and ended in 2012. So I hope it was. I think it was early in the history of working with artificial intelligence and buildings, but it's certainly not unique also, but certainly quite early. Good. So, and I assume we keep the questions for the end. I think that will be easier. Good. So, the second project, time-wise, involving artificial intelligence, was at the University of Columbia. So we go into something entirely different here. This is a project when I became the director of the Media Center for Art History. I learned about the fact that the department still had a huge slide collection that was there. We have 400,000, 35mm slides. We have 70,000 of the large lantern slides also that are still in the department. And they are hosted, at different places inside the department. There are space issues. These slides, cannot be kept there. So something had to happen with it. And I was thinking, well, what can we maybe do with this collection, to not lose the collection? And I'm going to honestly tell you also, on the one hand, it was interesting to digitize the collection so that, the images would be available again to people who wanted to use them. But at the same time, also a collection is something very specific because actually something that has been built by people, and it's sort of the memory of my department. So it tells us something about the faculty who were there. It tells us something about what they did. It tells us something, for example, when more interest there started to be more interested in non-Western art. So I thought it was really important to try to keep that memory. The problem is the size of the collection, 400,000 images. It would take a century to, well, I'm exaggerating, but take a very long time to digitize it. It's very boring to do also. And many images also don't really have, well, strictly speaking, don't really have a value, the same value as other images. So we were interested in finding out, well, is there a way to address artificial intelligence to find out what slides, are really valuable or really unique in this collection? So we received support from the Media Center received support from the Institute of Museum Library Services, and we started working, on a project, for digitizing these slides. So I'm just showing you an image of the drawers. There are tons of these drawers in my department. A wide variety. These are all 35mm slides. A wide variety of these images. What is, of value in this? What is, maybe less value? If an image is just taken from a book, we can go and make a better digital copy of it. So there's no real point in doing, making the effort to have a high resolution image of that image. These are the lantern slides, so the larger slides that were used starting end of the 19th century. Some of them are absolutely beautiful also, I must say. So, as I just said, we would like to determine the % of significant slides in the collection. Why would we like to determine this? Well, I have to convince people to tell them, okay, it is worth the effort. It's worth, to put the funds here in this project and to start this large digitization project. So, and because again, it's so complicated, is there a way that we can, automate also, and prioritize future cataloging of these images? So we worked on this. We used a number of technologies. I will go a little bit, I will be a little bit more brief here also because again, this was presented at the DH Nord and then should come out as a publication quite soon. But what I want to say is that the problem is, well, what makes a slide valuable? As I said, yes, what makes a slide valuable is probably if someone, if it's an original photo, then that image is valuable. How can you recognize whether a slide is an original photo? If I just go back to the previous image, or rather this one here, I'm sorry, here. Yeah, which one? Is it what is there? No, it's not really what is there. It's more, it's not what is photographed or what is in the image. It's more, again, does this come from a printed book or not? How can you recognize an image? And I talked to our digital curator at the media center, and you said, well, what I usually do, I take an image, I look at the image, and I kind of visually check if there is halftone in the image, because then you have those little dots from the printing process. Okay, well, tell a computer to find those little dots from the printing process. That was, of course, less evident. But luckily, what we found was that, and these are some of the technologies that were used, an article from 2011 using, we're looking into halftone image classification, so from AI, how it's possible to make a difference between images that have halftone or not. And actually, the way to do it is is using a Fourier transformation first. So we do some image processing, and then you will see that there is a specific pattern that appears in the image after the Fourier transformation. Namely, if there is halftone, you get these sort of star patterns. If there is no halftone in the image, you will only get one star right in the middle here. And then afterwards, the next step was rather easy, because then we could use a classifier, and some are off the shelf now. So use a classifier to classify the images with the stars and to separate them from the images without the stars. Okay, so it was like a two-step procedure. Again, I'm going a little bit faster. We produced first a reference set, because of course we have to train the system to be able to make a difference between these images with stars and images without stars. In addition, what we also did was that we used OCR to provide us additional information about it. Also, if on the label of a slide there is a reference to a book, well, that it comes from a book, for example. If there's a page number. So if you have, P30, well, I don't know here if there's one here, but anyway, it's it's possible to find out where it is. However, what was extremely challenging was the different type of fonts actually that you find for the different labels, because the collection was made over a long period of time. And in the end, what we did, is, well, here an example. So here, this one has halftone. You have these little dots. So, and here this one has no halftone. So this means that's an original photo. These comes from the previous images. This one has no halftone, just a star pattern. Halftone with different 4 stars there, meaning this has come from something that is printed. Feed this again, in the classifier. First it was a neural net that we used for this, and make a separation. Then afterwards, evaluate your results in true positive, false negative, false positive, true negative. True positive, for example, is, well, the computer recognizes it as something which has no halftone, okay? It's truly positive, and a visual recognition of the image said it's no halftone, okay? Then we have a true positive, okay? So we did that for about 8,000 slides. So on the one hand, we had always the computer will work, and then a human person who double-checked and verified it, compared both, etc. And this gives the statistical output on about 8,000 slides. And I will actually, this one I will well, skip it. I mean, again, we compared the three. We checked what the optical character recognition gave us, results. What the neural net model gave us results, and what finally, this was the last work from a graduate student at Columbia from the data sciences. He uses, gradient tree boosting, which is a technique from artificial intelligence, also and on the decision tree to find, again, to have the classifier, to perform the classification of the slides. And what we found is that, this is the ratio of the true positives. That means these are, if something was really a no halftone image, okay, and so then this would be the number that were correctly labeled as having no halftone over the total number that were visually seen as having no halftone. So here we found that it detected 59% of the total no halftone images. As you can see, the last one, the one with gradient, the decision tree model with gradient boosting, came to 64. The neural net here was the one that performed the best here at 80%. But on average, if you had the ones here with halftone here, that were, that gives a specificity, and again, it's the same ratio but then the other ones, you can see that, actually it's the last one that gives the best results. So what is next for this project? Well, this project is going on. What is next for this project? Well, it's basically using the three technologies and trying, to combine them to see on what set of images each one works best and see how we can even improve these results. Okay, so this will bring me to the third presentation. And as you can see, they're all very different. They're all very specific. In the second slide that I showed you, I said, every project is specific and there are many technologies that you can use. I think this is illustrating this well. So I'm going to go for something completely different now. I'm going to cross the ocean. Let me zoom out a little bit. And let's go first. How much time do we have left? We have about 5 minutes. About 5 minutes. So let me then go to Clermont-Ferrand. Okay, so let's go to the Cathedral of Clermont-Ferrand. A very different project, a much more archaeological project on this Cathedral of Clermont-Ferrand. This project was, is a collaboration with my colleague Michael Davis. And here we go. And actually where I'm going to take you is, if you have here the Cathedral of Clermont-Ferrand, the city of Clermont-Ferrand, I'm going to take you here on the roofs of the terraces of Clermont-Ferrand, because there is something very interesting with this building and very specific to this building, is that there are full-scale architectural drawings on it. So again, I'm jumping to something completely different. This is a current project. It will be published in an article, should be quite soon in a Festschrift. So let me take you there, and let me also show you one of the technologies that the Media Center is using, which are these virtual tours that we have. And sorry, the zoom little thing is right in the way here. Good. So let me take you here, for example. So we're jumping on the terrace of Clermont-Ferrand. And if you look at these terraces, and this is quite unique, you barely can see it, but if I zoom in, we can see this here. You see these lines? These are, scratched in the surface. So incised in the surface, and these are actually architectural drawings that are at life size. So they're as large as what they were going to build. So now let's take a look at them. So for example, what I just showed you was this section here, okay? So we chalked them up. We chalked them up. I mean, we're not this was maybe Michael who did it. So it's hard stuff for to do that all the time. I mean, already in the 1960s, I believe Robert Branner did the same thing. I mean, so they're known for a while. There is one issue with them, is conservation. They are slowly disappearing. But I think that the French authorities are now have a project to preserve them. Different types of elements. These are elements from a window. For example, this is a portal. So this is what we come, and actually this was also actually built also. But then there are some more mysterious parts, if I may say. For example, these arcs. You see we have these intersecting arcs here, and that's less clear, what this could be. Michael Davis, when he wrote his dissertation about Clermont-Ferrand, he had already, said that maybe this could be, the curvature of flying buttresses, of the flyers of the cathedral. The problem is, how do you verify this? How can you control this? And we have different sets of these arcs. So we have one here, one there in red, and then one single arc that is here. So what do they represent? What could they be? Okay, so well, first we went with a total station on the terraces of Clermont. A total station is an instrument like you sometimes see on the side of the road. It lets you take precise points in a three-dimensional space and then feed them in a computer. And here you have the circles that actually, so these how to say, highlighted dots are basically points that were taken on these arcs, and then we could recreate these circles that are there on the terraces of Clermont. So for example, this section in red corresponds to this element here, but then precisely measured. So that was number one. 20 years ago, without a total station, or 20 to 30 years ago, without a total station, it would have been pretty cumbersome to measure them. It's possible. I'm not saying that it's impossible, but it would have been pretty cumbersome. In addition to that, and that is newer, is that we now have photogrammetry, digital photo, I should say, digital photogrammetry, which is different from the analog photogrammetry. What does that mean? Well, if you take photos from objects and you calibrate them, and you put them in a software, then you can get a model. But it's not just that it's a model to scale also, meaning that you can take measurements on these objects. Okay, so if you, for example, go for here, this one here, and 3, you're going to have see what you can. For I'm just taking this as an example. So I would like to have the distance from this element to this element. So I don't know why it's not showing me what's going on, or the thickness of this. Oh yeah, I've already had this issue. 1 second. So anyway, it's pretty easy to find accurate measurements here. I'm sorry, it depends on the browser that you're using. Sometimes this web-based software doesn't always work. That's the point that I want to make, is that basically having photogrammetric models of the flyers of the buttresses here made it possible for us, Michael and me, to compare it with here the diameter of these circle of the circles of which these arcs were a segment. And what we found was exactly what we had hoped to find, is that basically you have 4.48 meters for 2 of these circles, namely this one here and this one here, and we see that it corresponds here to the intrados of the voussoirs of the flyer also, showing that it's very probable. Of course, we cannot never know for sure, but it's very probable that these arcs were actually placed there to be models for what would be the flying buttresses. Is this important? Yes or no? Do I have 2 more minutes? Fine, good. Okay, so is it important? Well, actually, yes, because we say, okay, fine. We know that these circles, that they correspond, the arcs correspond, to the arc of the flying buttresses. That's nice to know. But what it also tells us basically is that these arcs were likely used, and this is illustrated in Villars de Honnecourt. For example, we know that medieval masons used templates, so they had like wooden forms, shapes that then afterwards were given to the stone cutters, so that they could use it in the quarry and prepare the stones and cut them correctly out, and then afterwards have the stones brought to the building site. So what we see likely here is something that is precisely part of this building process. So precisely part of how communication happened between what we would call the master mason or the architects, and then the stone-mason, and how they ordered these the stones for building these arches. It goes actually one step further. You have 1 more minute. Why are these arcs intersecting? There's no reason why these arcs are intersecting. Well, if you think about a flying buttress, for which you have a schematic view here, this is what you want to have. This is your wall. You want to have it nicely, abut against your wall, and get the thrust of your vault, so that that it helps the structure of your building. This is certainly not what you want to have, because what you're going to have, you're going to load your wall, and basically your whole building is going to collapse into the inside. Well, what these arcs, these intersecting arcs actually do is, if you think of it, say here you would have just, if they just had made circles, no intersecting arcs, this is what we would have. They would have different possibilities. They could have taken this as a flyer, perfect, it abuts fine against the wall, no problem. And this would be the maximum where they could go. Okay, but if they go beyond this, then again, you're going to put more pressure on your wall, which is not what you want to have. If you want to go 1 step further, okay, so again, we have this here. Now, what you can do is, if you want to have those limits of the amount of stones, voussoirs that you can put in there, well, why not push this interior arc circle a little bit outwards, make it intersect with the other one, and it gives you perfectly, the dimension of the maximum, span that your flying arc can have. So probably what we see here, it's not only, a system to have these stones built ahead of time, but also that they perfectly knew how many of these stones should I order, because this is expensive material, each of these claveaux or each of these voussoirs that they're going to put there, exactly know how many can I put there to have the maximum span. They knew how many flyers they wanted to have, so they knew how many stones they had to order, and also to make sure that they would not go over the edge and end up in the scenario where basically the flying buttress would be a structural problem instead of a structural helping tool. So, and here just another image of these flyers at Clermont-Ferrand. Good. There are more projects with the media center. I think this is. Yes, well, the main ones that I wanted to present to you, and I'm more than happy to take questions. Again, thank you for your attention.
Thank you.